Hi everyone. In this section I'm going to talk about potential energy, but before I get into potential energy, I want to talk about the difference between conservative and non-conservative forces. Conservative forces are forces where the work done by the force is path independent. So this means that it doesn't depend on the path length traveled, instead it only depends on the initial and the final endpoint. Conservative forces do not change the overall total mechanical energy of the system. The two conservative forces that we'll focus on are the force of gravity and the elastic force, and we'll see that each one has a potential energy term associated with it. Non-conservative forces, on the other hand, are forces where the work done by them is path dependent. So this means it does depend on the path length traveled, and non-conservative forces do add or remove energy to the system and change the total mechanical energy. An example of a non-conservative force is friction. So for an example, if we were to push a box along a floor where friction is acting on it, the longer we push that box on the floor, the more energy will be removed by friction. Okay, let's start by looking at gravitational potential energy. Potential energy means stored energy. So gravitational potential energy is energy stored in a system due to work done by the force of gravity. So the term is PEG for potential energy, and the G means gravitational, equals the mass in kilograms times G, 9.8 meters per second squared, times the height h. Now the height is in meters, and it's the height above a reference point h equals 0. The choice of the reference point for gravitational potential energy is arbitrary, so you can choose that reference point. That means that the value of the gravitational potential energy at any point is dependent on reference point. So the actual value doesn't have a lot of meaning, but objects that are higher than other objects would have a higher gravitational potential energy. So we're going to choose h equals 0 for the problem. A standard choice is to choose the lowest point in the problem as h equals 0. For example, you can think about yourself, maybe you're in a room and you could choose the floor as h equals 0. Or you could use the reference as the ground outside as h equals 0, which might be at a different height, and both of those are valid choices. So though this is dependent on reference point, where we choose h equals 0, that will be the reference point for the potential energy to equal 0. And the change in potential energy, delta PEG, equals mg delta h, the change in height, and this is independent of reference point. So no matter what point you choose for h equals 0, we'll still have the same change in potential energy as an object is moved through a vertical displacement delta h. Okay, let's look at some examples. Example 9, an 80 kilogram skier skis down a ski slope with a length of 212 meters and winds up undergoing an overall change in elevation of 30 meters. Determine the skier's initial potential energy, final potential energy, and change in potential energy if potential energy is measured A at the elevation the skier started at, B at the elevation the skier ended up at. Okay, so this question is giving us two options for h equals 0. In part A, h equals 0 was at the top of the hill. So this point here. And then we want to find our initial potential energy, final, and the change in potential energy. So using this choice here, we have initial potential energy is mgh naught. That means that h is 0 at this point, so the potential energy must be 0 at that point as well. Then when we calculate the final potential energy, we'll have mgh final, so 80 kilograms times 9.8 newtons per kilogram. Now the height. If this is 0 here, then this is negative 30, so it still has to work like the y-axis where anything below our 0 point is negative. So negative 30 meters. And this gives negative 23,520 joules. Okay, so the change in potential energy, delta PE, will be potential energy final minus initial, which is going to be negative 23,520 joules minus 0. So we get negative 23,520 joules. So potential energy is lost because the skier moves down to a lower height. Now let's try part B, where we're asked to put the bottom of the hill as h equals 0 for part B. That's the natural choice, I would say, the lowest point in the problem. So in this case, our potential energy initial at the top of the hill is not 0. So this is no longer 0. I'll just cross that out so it's not confusing. 0 is at the bottom. This is at a height of 30. Okay, for part B. So this is mg h naught, which will be mass 80 kilograms times 9.8 times positive 30. So 80, 9.8 times 30. And I was kind of showing you that it's the same that we had over here, but the sign is changed. So this will be 23,520 joules. Now the final potential energy is 0 because it reaches a height which is at the 0 reference point. So the change in potential energy is final minus initial, and final is 0, so we get negative of the initial, negative 23,520 joules. So you can see that the actual initial and final values changed based on the choice of reference point, but the change in gravitational potential energy was independent of reference point, and that is why this quantity is useful, and we'll see how it's used in our next section on conservation of energy. Example 10, a 4-kilogram rock is lowered from a ledge 6 meters above the ground to a ledge 2 meters above the ground. What is the change in the rock's potential energy during this process? Suppose you were then to raise the rock back up to the 6-meter ledge. How much work would have to be done on the rock by an applied force to accomplish this? Okay, so for part A, we want the change in potential energy, delta PEG, for the rock. It's mg delta H. And we can find that. We can choose the reference point as the lowest point in the problem, or any point. I'll choose the ground here. So I'll have m, 4 kilograms, times 9.8 newtons per kilogram, times delta H. If I chose here, it's moving from this point, that's the initial point, to the final point here. So I'm going to have 2 meters minus 6 meters for the height difference. So that's negative 4 meters, and this gives negative 157 joules. Okay, now how much work is done? We're lifting it back up, and there's an applied force here of Fa. If it's just lifted at a constant speed so that there's no acceleration, then we're going to have these forces balanced so that Fa, this is part B, equals Fg, which is mg. Then the work done by this applied force would be Fa d cos theta. It's in the same direction as the displacement, which is up, so we have cos of 0, which is 1. So this is FAD, which is mg times d. And notice this is 4 kilograms times 9.8 newtons per kilogram times the height difference, which is 4 meters. It's moved up 4 meters. And this is the same expression that we had above for the change in gravitational potential energy. So this gives positive 157 joules. So you can see that in lowering the rock, it lost 157 joules of energy. To just lift it back up to the same height, the applied force would need to replenish that 157 joules of energy. In order to look at another type of potential energy, elastic potential energy, we'll need to look at the spring force. The spring force is the force exerted by a stretched or compressed spring. In fact, it doesn't have to be a typical spring that you can picture using in a lab. It could be any material that has any type of elasticity. Hooke's law gives an expression for the force exerted by the spring, Fs in newtons, equals negative kx. K here is the spring constant, which is measured in newtons per meter. It's also called the force constant, and it gives a measure of the stiffness of the spring. Then we have x, which is the displacement of the spring, from x equals 0, which is its rest or its equilibrium length. So that's the natural length of the spring. This isn't arbitrary, that's a fixed 0 point. Then the displacement from that point is the amount of stretch or compression that the spring undergoes when it exerts this force. And notice there's a negative sign in the vector definition. This negative sign is there just because the spring force always acts opposite to the displacement. So if you were to stretch and pull a spring away from equilibrium, it would exert a force back towards equilibrium to return it to its rest length. The elastic or the spring force is a really interesting force because it's the first example of a variable force that we've seen. The other forces we've looked at, gravity, friction, applied forces, have all been constant as an object moves over a displacement. Since the spring force, Fs equals negative kx, it depends on the displacement and changes as the object moves. So in this case, the work is equal to the negative of the area under the F versus D, or the force versus displacement curve. This is a very general definition of work, and it relates to an integral. It's a bit more advanced than we need for this course, but I wanted to show you where it comes from. And this form is a simplified version that applies to constant forces only, so we can't use this for the spring force. And that's the important part to remember, is that this definition of work doesn't apply to the spring force. So if we plot the spring force versus displacement, it's negative kx, so it's linear, and the slope equals negative k, so it looks like this. The area under the curve is a triangle, and this is for a spring that started at 0, its equilibrium position, and extends to a distance x. Area is 1/2 base times height, and it's negative of the area. So we have negative 1/2 x times the height, which is the force, kx. And multiplying that in, I have negative 1/2 kx squared. Now, also a bit beyond our course is this relationship that the work done by a spring is negative of the change in elastic potential energy. So the important result from this that we need to work with is that elastic or spring potential energy, PES, equals 1/2 kx squared. So this is the displacement, again, the stretch or compression of the string, and it's measured in meters. Then I have the spring constant in newtons per meter, and that gives us the elastic or the spring potential energy in joules. Now this has a fixed 0 point, unlike gravitational potential energy. The elastic potential energy equals 0 when the spring is at its equilibrium or its rest length. Then we can also find the change in elastic potential energy by taking the final elastic potential energy minus the initial potential energy. And if we want to find the work done to stretch or compress a spring, it's going to be this value as well. So this will be the work required to stretch or compress a spring. Example 11, it requires 6 joules of work to stretch a particular spring by 2 centimeters from its equilibrium length. A, what is the spring constant? And B, how much additional work is required to stretch the spring an additional 2 centimeters? Okay, so for A, just simple use of this elastic potential energy formula, which is 1/2 kx squared. And again, that's the amount of energy required to stretch or compress the spring. So that's going to be that 6 joules. Then we can solve for K. K will equal 2 PES over x squared. So 2 times 6 joules divided by 0.02 meters squared gives me 3.0 times 10 to the 4 newtons per meter for the spring constant. All right, how much additional work is required to stretch or compress the springs? An additional 2 centimeters. So this will be delta PES, which will be PES final minus initial. We know that this initial value is 6 joules. It was already stretched 2 centimeters, which required 6 joules. So we'll have the final value 1/2 kx squared minus 6 joules. So that's going to be 1/2. K that we found, 3.0 times 10 to the 4 newtons per meter. 0.04 meters squared, since now it's compressed to 4 centimeters, minus 6 joules. And this gives 18 joules.